Mr. Hofstede here, coming live at you from my house, giving this the first go. Hopefully this video format and the YouTube channel and the live stream all works out good for you. So let's take a look at lesson 3. Lesson 2 we were covering Newton's first law, all centered around inertia. That will be important, that will be tested on. You have to know each of Newton's laws and a good summary of each of them. So if Newton's law was all about inertia and objects at rest tending to stay at rest or not accelerating, right? That's kind of the gist of that one. Here in lesson 3 with Newton's second law, we are talking about accelerated motion, which requires an external force or some net force that is not equal to 0. So, if an object experiences unbalanced forces, the object accelerates in the same direction as the net external force. We can rearrange this super popular, super famous equation, force equals mass times acceleration, to solve for any one of those three variables. Acceleration is force net divided by the mass, or acceleration or mass could be F net divided by A. Right? Where mass is scalar, you can't have a negative mass, right? It's non-directional, it's just a magnitude. But our force and our acceleration are both vectors, right? We see their little hats there, and we need to pay attention to direction and our reference system as a result. So the units for a force are a Newton. Covered that in Science 10, it's been a while. So let's break up what a Newton really means. So if force is equal to mass times acceleration, the units of a Newton need to have the same units. So the mass is measured in kilograms, and the acceleration is measured in meters per second squared. All of these are standard or SI units. So our kilograms times meters per second squared is equal to 1 Newton. And that's another important derivation and a great way to check your work to see if all of the parts are adding together, the units are matching up, and we are coming up with a mathematically correct answer. Alright, the acceleration, which is equal to the net force divided by the mass, depends on two things. Obviously, the net force and the mass. So, we're going to take a look at this. I'll try to zoom you in a little bit on this one so you can see clearly what's going on. When we're talking about acceleration, right, we want to see how acceleration can be changed, right, how it is affected by, in this case, the net external force. So our manipulated variable, right, what we're going to be changing, so that MV means manipulated variable, and that will always be what we are changing. So in this first point, our manipulated variable is our net force acting on our object. And we are hypothetically, right, doing a little experiment here. We're changing how much force is applied to something, right, even if we're just looking at a nice Norwex pen here. We're going to see how much the force, right, as I push it, will change the acceleration. Right, different force means different acceleration. So our responding variable, right, would be our acceleration. We're looking at how acceleration depends on these other factors. So if we're doing a good science experiment, we only want to have one manipulated variable and one responding variable. Right, RV is responding variable. So we're going to have to control the third independent variable, which is our mass. Alright, so when we do experiments where we change the amount of force applied to an object and measure its resulting or responding acceleration, we're actually going to get a nice linear graph. And that has to do with its proportionality. Right? So we're looking at this relationship, right, coming straight from the general formula. Acceleration, right, is equal to F net over m. We can see, since both acceleration and net force are on the numerator, they have a direct relationship. There's no constant there or anything. So we have a direct relationship between acceleration and mass. So we can summarize that saying acceleration. Sorry, this is really shaky. My table is not the most sturdy in the world. It'll be better once I start using the whiteboard. So acceleration has a direct relationship with F net. And if we go back to our notes from our math skills, there was stuff about proportionality in there, right? And just reviewing that, we have a proportionality symbol. So since acceleration is directly proportional to the net force, we're going to state its proportionality using this little fish symbol, lowercase alpha. It's proportional to the net force. So what that essentially means is, if our net force is increasing, acceleration is increasing. Or if F net is multiplied by 5, acceleration is also multiplied by 5. They have a direct relationship. As soon as one goes up, the other goes up equally, and vice versa. One could go down, the other would also go down. Alright, so that just comes to us from this general formula. The relationship between acceleration and our net force in this equation, right? Since they are both in the numerator, they have a direct relationship. Alright, let's look at something different. Now we are seeing how the change in mass will affect our acceleration. So once again, acceleration is a responding variable, but now our manipulated variable is the mass. So similarly, we only want to be changing one and seeing its result on the other, holding the third variable at a constant or our controlled variable. So we'll have to have a constant net force and see how changing the mass will affect the acceleration. So now we don't have both of these quantities in the numerator. Acceleration is in the numerator, whereas mass is in the denominator. Sorry if you're getting motion sickness from my bouncing around table and document camera. Maybe I'll have to get a new table. Alright, so now we're looking at the relationship between acceleration and mass. One on the numerator, one on the denominator. So their proportionality is acceleration is proportional to 1 over the mass. So instead of being directly proportional, like net force, mass is inversely proportional, or has an inverse relationship. Mass has inverse relationship. Proportionality is another way to say it. So what this means is, if our mass is increased, then our acceleration will decrease. makes sense. If we're applying the same force to, right, something really small, I don't have much small things, this clip versus this giant water bottle, which doesn't even fit under the document camera fully, right? So same force, we're accelerating the lighter object a lot faster. So as mass increases, acceleration decreases. Always good to come back for some logic tests. So what this means mathematically, if our mass is multiplied by some value, we'll say 3, then acceleration is divided by 3. Right? Another way would be times 1 over 3. And when we graph any inverse relationship or inverse proportionality, maybe you've done graphing in math recently. If not, you can punch this in your graphing calculator at home, and you'll see that we have this nice curve going down, 2 asymptotes, the x and the y axis. There's our inverse relationship graph. Okay, proportionality is usually one of the harder parts for students to really understand, so spend some good time going over this. Ask me any questions you might have about these ideas, about proportionality. I'll try to explain it to you if this wasn't clear, but it really boils down to, right, understanding within a formula the relationship between different variables, right? Whether they're both in the numerator, direct relationship, one in the numerator, one in the denominator, we have an inverse relationship. So we're essentially removing the control variable from our calculation and writing our proportionality statement and understanding that mathematically, as we change one, it will change the other either directly, the same, or inversely, right, with our opposite operation. Okay, let's try out our first example. I'll do it on the whiteboard. Hopefully we have less shakiness happening, but you never know. Okay, so example 1, we want to take a look at this object. We often will just call things objects. You can try to make it more exciting for yourself by coming up with a better backstory for this. Maybe it's a basketball. So it's accelerating at 24 meters per second. If the net force is tripled, the mass is doubled. What is the new acceleration? So we have to look at our proportionalities. Since our acceleration is directly proportional to the net force, right? There's our direct relationship. That's off your screen. Okay. We know that if our net force is being tripled, which is the same as times 3, then acceleration is being tripled times 3. Alright, on the other hand, we have acceleration inversely proportional to mass, right? Or it's proportional to 1 over m. So this is our inverse. If our mass is multiplied by 2, we're doubling it, then acceleration is multiplied by 1 over 2, or divided by 2. Alright, now we're going to bring it all together into our new acceleration. So our new acceleration, right, has this adjusted net force and this adjusted mass. We started at 24 meters per second squared. We're going to have to multiply it by 3 and multiply it by 1 over 2, or divide all of that by 2. and that comes out with a new acceleration, which is equal to 36 meters per second squared. Alright, so when we're just looking at acceleration is equal to net force. Sorry, I ran out of room. I got a new whiteboard. When we're doing proportionality, the easiest way to think about it is from our general formula. So we're looking at acceleration, which is starting at 24, right? And we know that we have to multiply by 3, right? We're replacing our F net with 3 times F net, and we're replacing mass with 2m. So if 24 is equal to our starting net force and starting mass, we have to now adjust. This is our new kind of adjustment factor. So our acceleration will be 24 times that inserted, right, new net force and new mass, which is 36. Right, so we can always just substitute the values into our general equation, right? Replacing our starting net force with 3 times the net force and our starting mass with 2 times the mass, and multiplying it by our starting acceleration. Alright, let's give our next example a shot. This is a longer lesson. Hopefully you're keeping up, following along with me. We have a 15 kilogram block, so we know the mass. It's pushed to the right with a force of 48 newtons. We want to determine a new force on it, knowing that its acceleration is 1.8 meters per second squared to the left. Alright, so let's start by drawing out our box, our object. A free body diagram or a force diagram. We know we have 48 newtons to the right. We'll call that F1. We have this unknown force to the left, F2. That's what we're trying to solve for. And we also know that its overall acceleration, right, this box, it will be accelerating at 1.8 meters per second squared. Okay, just get a quick reference system. We'll say that right is positive and left is negative. Okay, so we have to find the second force, and in order to do that, we need to know the net force of both of them. So we have a 15 kilogram box. We know the acceleration, we know the mass. We're looking for F net, which is equal to mass times acceleration. Right? F net will be broken up into our two forces. So we have F1 plus F2 is equal to our mass and our acceleration, where our F1 is known as positive 48 newtons plus our unknown F2 is equal to 15 kilograms, the mass of the box, times the acceleration, which is to the left, so we need to include that negative. Alright, so we have to isolate for F2 by subtracting 48 from both sides. We know that F2 is now equal to 15 times 1.8, that'll be negative, minus 48. So we're going to have a really big negative number. So that becomes negative 48 from this plus 15, negative 1.8. And our resulting force, that is to the left, is 75 newtons. 75 newtons left as our final answer. Right? That's all the question was looking for. We want to determine that second force, F2. Okay, hopefully that makes sense. We're just working with this brand new equation. Not brand new, it was part of Science 10 briefly, but new for Physics 20. Alright, we got one more example. It's a long lesson today. Our third and final example is a really long, complicated vector question. 2D vector, going to be doing trig. I might get out my chart again. So in this question, we know the acceleration. We know 2 out of our 3 forces. We're trying to find that final unknown force. Okay, there's my nice table to keep everything organized. So we are starting with a 2 kilogram box and 3 external forces. The mass, we have this first force, which is 150 newtons, and it's going at 25 degrees. We have this second force with an unknown angle and an unknown magnitude. And a third force that is fortunately a one dimension. We have 80 newtons just to the right. Okay, so the question tells us that the overall acceleration is to the west. So we're going to use our northeast as positive, southwest as negative, and we know we're accelerating to the west at 35 meters per second. Meters per second squared, that is. Alright, here's our setup. So, let's bring it onto the table. We have F1 plus F2 plus F3 is equal to F net. So, all of our acceleration is going in the x direction. So that means we know that our y component, right, our vertical component, is going to have no net force. That's a good starting point. So the force in the y direction from 1, 2, and 3 has to equal 0. And our net force in the horizontal direction, right, we can determine by using Newton's second law. Let's do that quick here. So in our horizontal, our F net is equal to the mass and the acceleration. Right? Where we know the mass and the acceleration, it's 2 and negative 35. So our net force is negative 70 newtons. So that's a good starting point. Everything in our x direction has to add up to negative 70 newtons, or 70 newtons to the west. Right? So that actually means that our net will be 70 newtons west. Okay, from our vector diagrams, our F1 is going to the northwest. That'll be our x1, y1, and the angle is given as 25 degrees. Our F2 is our unknown, but we know it has to be something to the southwest. Right, and that'll be our x2, which is unknown, and our y2, which is unknown. Right, we can't figure those out until we, work backwards from our net force. A little complicated. Hopefully once we work through the question, that's a little more clear. And our third force, F3, is 80 newtons to the east. Right, so that one's easy. We know we have positive 80. We know we have 0 in the y. Alright, let's break up our F2 into its components. So for x1, we know it's going to be to the west, which is negative, and it's our adjacent side, so we're going to use cosine of 25. Right, cosine is adjacent over hypotenuse. We know 150, so we're going to multiply both sides by 150, right, and solve for x, our adjacent side. Y, we're going to the north, that's positive, and it's our opposite, so we're going to use sine of 25. Alright, we can solve for our unknowns now. Right, that's going to be our x2 unknown and our y2. So we have these equations set up. So let's start with the horizontal. This isn't what I wanted. I'm going to separate it, but we're still looking at the horizontal component. We know that x1 plus x2 plus x3 is equal to negative 70. We're solving for x2, so we're going to subtract both sides. By x1 and x3. And we can solve for it. Negative 70. Oh, gross. Negative 70 minus our negative 150 cosine 25 minus our 80. And that'll come out as 14.5 to the west. Negative 14.05. Right, so we can write that in here. And we have to do the same thing in the vertical, but I'm not actually going to write it out. We know that our net force is all going towards the west, right? Our acceleration has no north or south component to it. So we need to have 0 net force. We know that the third force has 0 vertical components. So our second force, our unknown force, needs to be opposite our force in the y direction from our first force. So that'll just become negative 150 sine 25. Right? When we add everything in this row up, we end up with 0, which is what we need. Okay, now we can determine the magnitude and the direction or the angle of F2. I'll try to just fit that in here. We know we're going west, we know we're going south. That's good, that's how the drawing had it shown. We'll start with the west. of negative 14.05 newtons, and our south, which is negative 150 sine 25, which when you calculate it is negative 63.39. Not a bad idea to store those in your calculator, right? Maybe I'll call that A, I'll call that B as I'm going through the calculations. And we're looking for F2 and that angle. I ran out of room. Let's try doing it down here. So F2 is equal to, in magnitude, square root of our first side squared plus our second side. I kept the negative signs around, but since we're squaring them, no harm, no foul if you leave out those negatives. And that will come out as 64.9. Right? And we're looking for this angle. We're going to use our opposite over adjacent, our tangent, inverse function, arctan, where the opposite was our 63. Don't worry about the sign actually. When we're doing these, we'll determine the northeast, southwest direction just from our diagram. So we got 63.39 divided by 14.05, which comes out as 77.5 degrees. And from our diagram, as I've drawn it, maybe you drew it like this, you're going to have the other interior angle, which will be 90 subtracted by 77.5. But as I've drawn it here, we're going from the west towards the south, so we are south of west. Okay, so F2 is equal to 74.9 newtons at 77.5 degrees south of west. Really long lesson, really long examples, but give that homework a go and let me know if you have any questions. Thanks, guys. Talk to you soon.